Today we are going to talk about specifically binomial distributions and binomial probabilities. What does binomial mean? Well, that means the probability that something either happens or does not happen. That's it. It either does or does not. So that's what we're talking about when we're talking about binomials. Got to share my screen here. There we go. And change cameras. Come on. There we are. Cool beans. Where's my stylus? So now it's time to talk about a special type of discrete random variable, which is applied to sampling with replacement. Is there a way to do this without replacement? Yeah, I think there is, but we won't do it in this course. So, whew, thank goodness. Okay. Probability distribution associated with this is called binomial probability, and we've already talked about that means it either is happening or it is not. Binomial experiments. Consider an experiment with two possible outcomes. We're going to say that these are success or failure. Now, success doesn't mean that it was a good thing, and failure doesn't mean that it was a bad thing. Success just means the probability that success means it occurred. Failure means it does not occur. Okay? Because I could say something like, the probability a student fails a test is 20%. I pick 5 students at random. What's the probability that 3 of them fail? You see, in that situation I just set up, failing the test was success. Because success is just the item you're looking for. It either happens or it does not. So it happens, that's success. It does not happen, that's failure. Repeating this experiment in a number of independent trials is called a binomial experiment. The probability of success, little p, must be constant for all trials. So let me say that again. The probability is not allowed to change from trial to trial. That's why it has to be with replacement. You see, without replacement, now it's not the same probability from trial to trial and things go wonky on us. Since success and failure are complements, remember they should always add up to 1, the probability of failure would be 1 minus p, or 1 minus the probability of success. Also, must be constant. Random variable capital X is the total number of successes in N trials. A bag of marbles has 2 red marbles and 3 green marbles in it. That's 5 marbles. Each time you pull out a marble, it's either going to be red or green, because that's all that's in the bag. The chance of getting a red marble is 2/5, and the chance of getting a green marble is 3/5. Let's say that red is success and that green is failure. If you do that, then you have a binomial experiment. So little p would be the chance of success, which means little p is the probability of pulling a red, which is 2/5. That means probability of green is 1 minus 2/5, which is 3/5. You're going to pull 3 marbles from the bag with replacement. That means n equals 3 because there were 3 experiments, 3 iterations of the experiment. Let the random variable capital X be the number of successes, which means reds. That means capital X can have 4 different values, 0, 1, 2, or 3. Notice I gave you all those letters there. That's our tree diagram. We're going to make a tree diagram. Very first marble was either going to be red or green. Red or green. The probability it was red was 2/5. Probability it was green is 3/5. Guess what? Because it's replacement, every time you draw a stick to an R, that's 2/5. And every time you draw a stick to a G, that's 3/5. So let's go ahead and finish up the tree diagram. And I'll have to build mine from the bottom up because I don't have as much vertical space as you do. This is a big tree diagram. Oh boy, there we go. It hasn't told me to do so, but in the space that I've left to the left of this tree diagram, we're going to find the probability that X takes on those 4 different values. So probability that X is 0. Okay. The board is struggling today. Don't write too fast or it won't work properly. There we go. So probability x equals 0. What does that imply? That means you pulled 3 green marbles back to back to back. So this is the probability of no red or 3 green. How does that happen? Well, if you followed the tree branches down the bottom of the tree, you would get no red marbles. You'd get green, green, green. So that's 3/5 times 3/5 times 3/5. Which is 27 out of 125. I do want to write this, though. It was 3/5 squared. Just going to be making a cubed, excuse me, yes. I can fix that. 3/5 cubed. There we go. Okay. Probability that capital X equals 1. Oh man, okay. So that's 1 red and 2 green. And guess how many different ways that can happen? That can happen 3 different ways. This would be red, green, green, plus, because or, green, red, green, plus, because or, green, green, red. But because the probabilities are reset from trial to trial, because this is with replacement, the nice thing about this is those 3 different events all have the same probability of occurring. So that makes life pretty easy, doesn't it?
Sure.
Okay, that's going to give me 2/5, because that's the probability the first one was red. And then times, well, the next 2 is green. So that would be 3/5 squared. Add because it's an or statement. It could have been red, green, green, or green, red, green, or green, green, red. Anytime you say or, it's an add. And by the way, order doesn't matter. There were 3 different ways this could have occurred. So you know what? I'm not even going to find that probability. I'm just going to leave it like that. That makes me happy. I'll just leave it like that. You'll see why in a minute. Let me repeat myself.
I know, never mind, it's because there's 3 different ways.
Okay. I found the probability of 1 and then realized that all 3 of them have equal probabilities. Well, the probability that capital X equals 2 means that there was 2 reds, but you know what else that means? That means 1 green. That means 2 red and 1 green. So in the example we just did, the red went to 3 different places. Well, for this one, it would be the green that goes to 3 different places. So this would be probability of red, red, green, or red, green, red, or green, red, red. Again, all 3 of these are going to have equal probabilities of occurring because we replaced this marble every time we pulled one out. That means I only have to find the probability of 1, and I get to multiply it by 3 again. So red, red, and then green. Red, and then red would be times 2/5 again. So let's just say 2/5 squared. And then green, which is 3/5. And yeah, it happened 3 different ways. Notice I haven't even asked a question yet. I'm building up to some kind of grand thing here. The last one is probability that x equals 3. Use up every bit of this vertical space. You know, 3 means 3 reds. So that is the probability of red times the probability of red times the probability of red. That is going to be 2/5. Oh my gosh, this board's killing me today. Come on, active panel. 2 divided by 5 cubed. So I didn't write it. But at the very top, that 3/5 cubed, couldn't I have said that that was 1 times 3/5 cubed? I could, right? Just like down here, I could call this as 1 times 2/5 cubed, right? And then the 2 in the middle both happen 3 different ways. So there was 1 way, 3 ways, 3 ways, 1 way. 1, 3, 3, 1. That string of numbers sounds really familiar. Go ahead and flip the paper over for me. Well, here it is all written out for me. Yeah. Oh, it's just the binomial expansion from the binomial theorem last year. Yeah, 1, 3, 3, 1. Those, she just gave me the middle finger. Those are the coefficients of the binomial expansion of row 3 of Pascal's triangle. So yeah, binomial stuff is not going away. It has come back to haunt us. Yeah, and look what happens.
Why didn't you tell us that before?
Because I wanted it to be a grand realization that it is nothing but binomial expansion again. The binomial theorem. The binomial theorem that we used way back last year in Unit 7 comes back again in Unit 23, giving us the probability distribution function for a binomial situation. Hey, pay attention.
Sorry.
The binomial probability distribution function is in choose R in trials. And you okay?
Yeah.
Okay, anyway, n choose R, where n is the number of trials, R is the number of successes, and n minus R would be the number of failures. Lowercase p stands for the probability of success, and 1 minus p, probability of failure. Now, for small values of Pascal's triangle, like the one we just did, or the small values of R, we could use Pascal's triangle. Like the one we just did, we could have just used Pascal's triangle because it gave us the binomial coefficients of 1, 3, 3, 1. But what happens when we're talking about larger situations? There was 100 trials, and you were trying to figure out if 40 of them are going to occur. Drink some water or walk around. It'll help. Trust me. You could use Pascal's triangle. Oh, gosh. My goodness. So part A says to expand this binomial. It's got a power of 5. That's row 5 of Pascal's triangle. Oh, yuck. I mean, I gave it to you up there. It's 1, 5, 10, 10, 5, 1. Oh boy. Here we go.
Easy.
I'm going to do my best to make it fit.
Make it fit. What do you mean?
Alrighty. We have 9/10
I thought you only did
plus,
the second one.
no, we're expanding the binomial. It's going to have 6 terms. Remember the whole t sub r plus 1? It's going to be 6 terms here. The first term is 9/10 raised to the 5th power. There's the 1. If you did that, it would just be 1 to the 5th power. But this is being used for probabilities. Okay.
But this one is
1, 5. Now we take, oh my gosh, this panel. Oh my God. You decrease this exponent by 1. But the other one, which was 1/10, it gets the 1 that we took away from the 9/10. So it goes 1, 5, 10. We're just going to keep subtracting a power away from 9/10 and adding that power to the 1/10. 1, 5, 10, 10. Yeah, it's not going to fit.
5, 10.
And then 5, 1. So close. Now what I'm going to do is I'm going to use a little bit of active panel magic, and I'm going to lock the page if the computer will ever respond to me.
No, we don't have active panel.
Well, I told you it was going to be tough to make it fit.
You know what? Whatever.
So we'll just do this. Zzz. We'll let the math get skinny. There. Let there be skinny math. Wow, it's struggling. Wow. And then the last one is going to be 1/10 raised to the fifth power. Because I forgot my 4 there. Well, I didn't forget it. I didn't have space for it. And 1/10 to the 5th power. Holy crap. But do you know what all 6 of these things represent? These 6 terms represent probabilities that x equals some number. They're probabilities of something happening. Okay, part B says an archer has a 90% chance. Oh, 9/10. An archer has a 90% chance of hitting a target with each arrow if 5 arrows are fired. Determine the chance of hitting the target a certain number of times. So the probability of hitting twice only, that is probability that capital X equals 2. That means 2 successes and 3 failures. 2 successes and 3 failures is occurring right here. That's 2 successes and 3 failures. So that would be 10 9/10 squared, 1/10 cubed, which gives me 0.0081. Now, Gavin, what's your question?
Okay, never mind. I don't get it.
Okay, but can you ask a question? I don't understand. I don't get it. What part did you not get?
So why is it that one?
Well, it says 2. 2 arrows hit, right? Well, I mean, that's what it says.
All right.
Okay. The probability an arrow hits is 90%, right? Which is 0.9, which is 9/10. So what I did was I went to the place where 9/10 has a power of 2, because that means it hit twice. Yep. And that can happen 10 different ways. That's what the 10 on the front represents. Yeah, well, luckily we don't have to list them all out. But landing twice and missing 3 times happens 10 different ways. So the probability of hitting exactly twice is 0.0081. Very, very slim chance that it hits exactly. That probability that it hits twice only should be very slim because this person is very accurate. What's up?
So if this is twice, it's not the second one in the.
No.
It's the 4th one.
No, it's the one where the probability of success, little p, had a 2, where little p had a power of 2, because little p means probability of success. So we needed to find the one place where the probability of success had a power of 2 on it.
Okay.
Oh. Yeah, but that's 3. Okay, so this one is 3 arrows hitting and 2 missing, because this is a hit and this is a miss, like that. Okay. BII says at most 3 times. So what does that mean? Probability that x is less than or equal to 3. Oh my golly. This board. Less than or equal to 3. Oh man. Okay, guess what that means? That means 0, 1, 2, and 3 all work. So I would have to add those up. Here's 0, 1, 2, and 3. Or you could just say 1 minus, since that happens 4 different ways, it would be easier to figure out the chance that you don't do it and subtract it from 1.
I thought that we were looking at the coefficient of the 9 and 10.
No.
What?
Okay, let me explain this again. The 10 tells you that there was 10 different ways that you could have hit the target twice and missed it 3 times.
I know I'm not talking, but like on x equals 2, we picked the one that the coefficient was 9/10
Squared.
power.
Yes.
So why aren't we doing that for the rest of them? For the x's?
Because it says at most 3. That means it could be 0, it could be 1, it could be 2, it could be 3.
Exactly. So why would you?
It's an or.
Why would you pick from the right side? Like the 9/10 to the second, and the 9/10 to the first, and the no 9/10. Because that's coefficient 0, 1, 2, and 3.
He's not talking coefficient, he's talking exponent. He's using the wrong term.
Yeah.
I
You
think that's
did
where the
to
confusion.
the fifth,
I'm
fourth,
confused.
and third, which would be higher than 3. Instead of from the 0, first, second, third, which would be down and less.
Am I wrong?
Oh, he says coefficient. Okay, he didn't mean coefficient. Okay, I see what you're saying. I've circled the wrong ones. I'll be okay.
Okay.
I had no idea what you're talking about because you were saying coefficients. Okay, sorry. So when x is less than or equal to 3 means x equals 0. Sorry, I was just circled.
I realized it was wrong, then you realized it, so you can shut it. Yeah, that really tripped me out. I thought I got the lesson, and then he circled those ones wrong. Wait a minute. That's why we ask questions. I think you just play virtual Star Wars with Caleb. Very good. Really got that. I kind of want to hit someone though.
This is what this means. Now that is 4 different things. I think it would be easier, rather than finding those 4 probabilities and adding them up, I think it would be easier to find the probabilities of 4 or 5 and just subtract that from 1. I mean, you're going to get the same answer. It doesn't really matter. So you hit it at most 3 times. That means everything to the right of this being added up. There. Those 4 things, everything to the right of that bracket being added up. Or like I said, you could just say 1 minus the front 2 things. And I would rather just say 1 minus the front 2 things because it's less work for me. So I'm going to say 1 minus, that's 1 minus the probability that x is greater than or equal to 4. Because that's only going to be 2 things, 4 and 5, which are the front 2 there. So that is 1 minus, and then you just have to write in those 2 nasty things.
Yeah.
So 9/10 to the 5th, and 5 9/10 to the 4th times 1/10. Anyway, everybody knows how to use a calculator. You get 0.0815. The 9/10 is because of the 90% success rate.
I know, but like the fifth.
Because, all right, listen.
Oh wait, I'm sorry.
Because I don't want to add up 4 numbers. I think it would be. I think it would be faster to find the probability that you hit 4 or 5, which is what those 2 things in the bracket show you, 4 or 5.
I know, I thought that you were going to get the last. Oh, you're doing the first 2?
I'm subtracting the probability of the first 2 because the first 2 say 5 arrows hit or 4 arrows hit.
Oh, I'm sorry. I did not.
Yeah, that's okay. It's my fault for misspeaking and circling the wrong things in the first time. All right. So, is this something that you would do by hand? No, you would never do this by hand. You would use a calculator for this. So part B of the lesson, I'm not going to be doing that crap by hand anymore. I'm just going to let the calculator do it for me. And that's why I was saying, break out your graphing calculators. So that's part A of the lesson. When you're doing part A of the homework, yes, you're going to have to do it by hand. So I will make sure not to give you very many of those because you never do it by hand. The binomial distribution can be handled by your calculator. So consider a binomial experiment for which P is the probability of success, 1 minus P is the probability of failure. There are n independent trials. The probability there are R successes and n minus 1 failures is this bad boy right here. That is the binomial expansion, the binomial theorem. And we're using it for binomial probabilities, where little p stands for probability of success, 1 minus p is failure, R is the number of successes you want, so on and so forth. The expected or mean outcome, oh look, expected values, of the experiment is still mu. It is still in P. X is the random variable of a binomial experiment with parameters n and p. This is what you write. And this says X is distributed as a binomial distribution with n trials and probability of success P. It's just saying, yeah, X is a binomial distribution. And you'd be surprised how often you get a mark simply for writing, oh, X is distributed as binomial with n and p, where you'd write a number for n because that's the number of trials, and you'd write a number p for probability of success. Often you get 1 mark. Why? Because your calculator is doing all the work for you. Calculator is doing all the work for you. So hooray for graphing calculators. Your calculator has a binomial probability distribution function, also known as, oh my god, this board.
How?
To write slow. If we don't write slow, it draws jagged. The binom PDF. That is what the calculator calls it. You are not going to write binom PDF on your test. You are not going to write binom PDF on your IA if you use this stuff. This is calculator language, but that's what it looks like on the calculator. So the probability, when we did in part A, we said, oh, find the probability she hits it twice, then we would have used the binom PDF and told the calculator there was two arrows hit, and it would have given us our answer. Now, for the next one, when I said, okay, at most 3, that means 0, 1, 2, or 3, and I had to add up 4 different things, well, see, the calculator would have done that for us. And it would have used the binomial cumulative distribution function. That's binom CDF. So the C stands for cumulative. Has anybody ever seen the movie and know the movie well, Zoolander?
Yes.
What direction can Zoolander turn? I said know it well. Anyway, he can only turn left. Yeah, blue steel, right? Or whatever. He can only turn left. I don't know. That's just what happens in the movie. The point is, notice that I said that P, the probability that such as P, and it says X is less than or equal to R. It's because the calculator can only go left. Okay? It can only do less than or equal to. So when the one we just did, where I said less than or equal to 3, it would have been fine. It would have said, yeah, cool. R is 3, no big deal. Or X is 3, 1 and 2, sorry. But what if I have to go bigger? What if I have to go bigger than that? Then what?
You turn left.
Okay, guys, so. You do 1 minus the complement. Yeah. So if you need to go to the right, you do 1 minus. Okay? The calculator won't do that for you. Don't worry, we'll practice it a lot. Oh, look here, unfortunately our calculators, they don't allow greater than or equal to R, so what do? Yeah, you find the complement. I mean, like it's right here behind me. You guys weren't even looking at it, but there it is right there. Okay? It's the complement. Yeah, all right.
I don't like to read things.
Yeah, me either. All right, so 72% of union members are in favor of a certain change to their conditions of employment. A random sample of 5 members was taken. And they realized that all 5 of those people have the same probability of being in favor, 72%. That means P, probability of success, equals 0.72. N, which is the number of trials, is 5. And x could be the numbers 0 through 5. There. Pretty. This is find the probability that 3 members are in favor. Well, we're trying to get all the marks we can get on the test, right? So here's what we need to say. We need to say something like x is distributed binomially with n trials, which is 5 trials, and probability of success of 0. I hate this. 0.72. There, that oftentimes that'll get you a mark just for writing that. Part A. Probability that x equals 3 is what that says. If you were trying to do this by hand, this is what you would have to do by hand. 5 choose 3, and then you have success 0.72 raised to the third, and failure, which is 0.28 raised to the second. Yeah, I don't want to have to do all that. So I'm going to ask my calculator to do it for me. No, it's 5 choose 3. Like, how many different ways could I choose 3 things from a group of 5 things? And the calculator will do it for us. So we go to our calculator. I said we go to our calculator. There it is. Okay, clearly I turned on my timers by accident. I must not have hit the calculator. Okay, you ready for this? You guys paying attention? You need to be able to do this. You see this blue DISTR? That's distributions. So second, bars. And since we say x equals 3, we are looking for binom PDF. There it is.
Why PDF?
PDF because you're trying to figure out exactly 3. Not less than, not greater than, exactly 3. The C stands for cumulative. So I'm just going to hit enter. What's that? So binom PDF. Number of trials. There's 5 trials. Probability of success, 0.72. The x value is the number that you want x to equal. We wanted it to be 3. And you just hit enter twice. Now I wish Vivian and or Harrison were here today. Oh, Vivian, you have an older operating system. Yours did it do that the way that I just did on the screen? Or did it just show up on the main screen and say binom PDF with the parentheses?
Well, no, it has the 5.72. Is that what you're asking?
Yeah.
Yeah, no, it has it.
No, no. Did you get the screen where it said with the 4 options with the paste button at the bottom?
Yeah.
Okay. I don't know if Harrison's would have because I don't know which operating system you guys are working on. And then you just hit enter one more time, and it's going to give us the probability this occurs. About 0.293. About 0.293.
Can you explain to me how you got that equation?
Yes, I will explain how I got the equation again.
No, because again, well, like
Yes.
I heard it the first time, but like it didn't like
Mm-hmm.
it's like the whole circling thing.
Mm-hmm. Yeah. Yeah. It's right there, the thing I put in a box. It's the binomial distribution, binomial theorem.
What is? I'm confused.
What is he confused by?
What is R?
It says right there. It says that R is the number of successes. You go up a little bit higher where.
So 3.
Yeah.
Okay, 5/3 times.
It's not 5/3. It's 5 choose 3.
5, 2, 3 times 0.72
To the third, because I'm looking for 3 successes, which implies 2 failures.
times 1 minus 0.72 is 0.28
Find the probability that at least 3 members are in favor. That means the probability that x is greater than or equal to 3. We have a problem here. Our calculator cannot do greater than or equal than. So what do we do? You do 1 minus, which is the complement. You do 1 minus, come on, active panel, please, God. 1 minus the probability that it's not greater than or equal to 3. What does that imply? What's not greater than or equal to 3? Less than or equal to 2. That's the same thing as saying less than 3, because we can't have decimal answers. But we want to do it like this because the 2 is the number that we're going to use on the calculator. Okay? Now, we could have found the 3, 4, and 5, those probabilities, and added them up. Our calculator is going to do that for us. Now, I don't know what kind of notes you want to take on this, but this is going to use binom CDF. And the reason why, CDF means cumulative. CDF tells the calculator, add these probabilities up, starting at the number that you gave me and the ones below it. So I go on my calculator, and I type in exactly what I just saw. 1 minus, and now back to distributions. This time we're using binom CDF because we needed to add up x equals 0, 1, and 2. Binom CDF. You hit enter. There are still 5 trials. Probability of success is still 0.72. And the x value is a 2. And that's why I wanted to say less than or equal to 2. Because if you put a 3 there, you get a wrong answer. Because it includes 3. It adds up 0, 1, 2, and 3, but 3 was supposed to be on the other one. And you get 0.862. Thank goodness for technology.
X value 2. Is that right? Yes.
C.
Wait, was it x equals 3?
No, it's x equals 2.
I was right. No, I'm sorry.
The reason why it's a 2 is because 3 was part of...
I know that I listened, she didn't.
Okay. The expected value? Remember, expected value is just NP. It's just NP, which is 5 times 0.72. That's going to give you 3.6 members. All right, that was painful, that was frustrating, and I hate this active panel.